Any specific questions that anybody has?
Could we do like difference in means and proportions a little
Okay.
bit?
So just kind of walking through the differences between them and then maybe some examples.
Yeah, like how to get the statistics and everything like that.
Okay. Let's share my whiteboard here. Chapter 5 covers differences in proportions. So this is 2 categorical variables. In our summary stat, we're looking at we have 2 summary statistics that we look at. We look at the difference in proportions. Or relative risk. Are the 2 different summary statistics that we look at. Do you want me to talk about interpreting those values or more just calculations of these statistics and stuff?
Could you do calculations first, please?
Yeah. So when we look at our theory-based methods, that's when we use the formulas. And to calculate the standardized statistic, we're always looking at, so for 2 categorical variables, we're looking at the standard normal distribution. So we're looking at a z-test where we take the difference in proportions minus 0 because our null, this would be indicative of the null value, which would be 0 because we're assuming there is no difference. And we divide by the standard error of the differences. This standard error is going to be the standard error calculated under the assumption the null is true. So to calculate that, we take the square root of p hat pooled, and I'll talk about that value in just a second, times 1 minus p hat pooled times 1 over n sub 1 plus 1 over n sub 2. Everybody good so far?
Yep.
Yeah.
Sorry, if I go to the next page?
One
Yeah.
second.
Okay.
Okay, I'm good. Thank you.
Okay, so to calculate that p hat pooled, we use our overall successes divided by N1 plus N2, where N1 and N2 are our sample sizes. So that's how we calculate that standard error under the null and our standardized statistic. To find our confidence interval, which is an estimation, or gives us an estimate for the parameter. We use our statistic, the difference in proportions, plus or minus the multiplier, which is always given. We always give multipliers, times also the standard error for the difference in proportions. But this standard error is a different calculation because this is not assuming the null is true. So we're going to calculate it using our 2 sample estimates, p hat 1 times 1 minus p hat 1 divided by the sample size for that group, plus p hat 2 times 1 minus p hat 2 divided by the sample size for that group. So those are the calculations for the difference in proportions for the confidence interval and our standardized statistic. Any questions?
Nope, just writing it all down.
Okay.
Same.
So what exactly, how would you get like your, the p hat of 1 and the p hat 2?
Okay, so p hat 1, so this would be, this is the sample proportion in group 1. So it's going to be our successes in the explanatory variable group 1 divided by the sample size for group 1. And p hat 2 are the successes in group 2 divided by the sample size for group 2.
So like if it said like 50 out of 100 people, I don't know, did something and that was your successes in group 1, it'd just be like the 50 over 100.
Correct. So I thought I had it open, but I don't. I was going to pull up, hopefully. I can't get my, oh, I think I have to stop my share a second. Ah. All right. So let's see if I can find an example really quick here. So this is posted on the Google Drive. So here's an example of difference in proportions. So here, are you able to see this final exam review?
Yep.
Okay.
Mm-hmm.
So they took a random sample of 1,018 Americans and they looked at their education level and their beliefs about evolution. So it says of 380 people who received only a high school education, 80 stated they believed in evolution. So here, like part B, it says calculate 3 proportions who believe in that should say evolution. So the p hat 1 for our high school, we're going to say 380 is the sample size for the high school group, and 80 is who said they believed in evolution. And then that p hat 2 for our college group with some college education, 638. So we'd take the 317 divided by 638. And then that p hat pooled is 80 plus 317 divided by the sample sizes. So 380 plus, sorry, my screen is being weird. 380 plus 638. Is that making sense?
Mm-hmm.
Okay.
Yeah.
So we could go back and talk a little bit about the difference in means.
Yep.
Mm-hmm.
Okay, so then chapter 6 looked at one categorical, one quantitative variable. So here we're looking at the difference in means. And this is different from what we looked at in chapter 7, because in chapter 7 we were looking at paired data. And this is independent groups. So again, do you just want me to talk about the formulas mostly?
Yeah, just like you did for the 2 categorical variables. Perfect.
Okay. So when we look at theory-based, again, that's what we're using our formulas for. Here we use a T distribution because our response variable is categorical, or sorry, is quantitative. So we're looking at a t-test. So we look at our sample statistics. So here's the difference in means minus 0 divided by the standard error for the difference in means. To calculate that standard error, we use our sample statistics. So I'll explain what S1 and S2 are in just a second. So S1 is the sample standard deviation, and these would always be given. Oops, standard. Deviation for group 1. And our sample standard deviation for group 2. And N1 and N2 again are just our sample sizes. Okay.
So what would S1 and S2 look like if we're trying to gather data for standard error?
Okay, so those are, let's say it could be like given in the output, or it could say that in the problem, it could say this is the mean for group 2, this group 1, this is the standard deviation for group 1. So let me show you on that same worksheet. I'm going to go back up here to question. Let's see if I get one on here. Here's one. So question 4 says researchers were interested in how different fuel economy was in cars made in Japan versus those made in the US. So they have a sample of Japanese cars and a sample of US cars. So obviously these aren't related. So this is independent groups. And like down here, it gives me the mean and the standard deviation. So this would be X bar 1. This would be X bar 2. This would be S1, and this would be S2. So it would be N1 and N2.
Okay.
And it could also be in the prompt, like it could say that the mean miles per gallon for US cars is 20.14 with a standard deviation of 6.41. Okay.
Will you ever have to calculate the standard deviation?
You will never have to calculate a sample standard deviation. You might have to look at an applet to find the standard deviations or the standard deviation of the null. You will have to calculate standard errors using those formulas. Okay. Oops. Okay, so that's calculation of the standardized statistic. I don't think I ever wrote that there, so I'll write that here. This is the standardized statistic. All right, then to find our confidence interval for a difference in means, we look at the sample difference in means plus or minus the multiplier times the standard error. And that standard error is the same as for the standardized statistic. So the only time it's different is when we're calculating differences in proportions or a single proportion. Okay. Do you want to review chapter 7? Or we could work on some examples.
Is chapter 7 the paired data?
Yes.
Is that what the quiz is on this week?
There is paired data on the quiz, correct. There's also some independent stuff on there too.
Okay. I'd be open to going over that if that's all right. I have class tomorrow, so I haven't fully covered it, but
Okay. So chapter 7 is looking at paired data. So this is looking at either matched pair study design, where they've been matched with certain characteristics, or repeated measures like we looked at in exploration 7.2. So a paired study design is where the outcome or the response for one individual would affect the response for another. So when we're measuring on two individuals, like heart rates, like we did in section exploration 7.2, it's a paired study design because you have two measurements on one individual. Again, kind of thinking about theory-based. Again, this is going to be a t-distribution to find the p-value because the t-distribution approximates our quantitative data. So our standardized statistic is looking at a t-test. Here we're looking at so this is important to kind of point out, this is the mean difference, where before in chapter 6, we were talking about independent, we were talking about the difference in means. So we use X bar D for our notation for the sample mean difference, minus 0, because there is 0 is our null value, and we divide by the standard error of the mean difference. And to calculate that standard error, we're using the sample mean difference, the sample standard deviation for the differences divided by the square root of n. So this is sample So again, this could be given to you, like just saying the sample standard deviation of the differences was this value, or like from the applet, you have the red and the blue distribution, and then you have the black distribution that's showing the differences, and it's on that output as well. To find our confidence interval, we're looking at the mean of the differences plus or minus the multiplier times the standard error of the differences. Okay.
So pretty much once we calculate standard error, we can pretty much use that throughout each equation, like for confidence interval technically, and plug in the number that we got for standard error X bar D from our standard statistic.
No, so this is this calculation.
Oh.
This total calculation. So that's not, doesn't mean multiplication. That this reads exactly like I was been saying it, standard error of the mean difference.
Okay.
So like we can look at an example and that might help with that too. Are you guys, do you have everything off this slide?
Yep.
Yes. Yep.
So I'm going to go all the way up to the first question here. Actually, let's just talk about the second question. So this is looking at like this stats course. So often parents of students that have had bad experiences with statistics courses and pass on their anxiety to children to test whether actually taking statistics decreases students' anxiety about the subject. The statistics instructor gave a test to rate student anxiety at the beginning and the same test at the end of this course. Anxiety levels were measured on a scale of 0 to 10. Did the data indicate that the anxiety levels about statistics decrease after students take a statistics course? So does this appear to be a paired study design or independent groups?
It's paired, right?
Yeah, and is it paired with repeated measures or matching?
It's repeated measures.
Yep, because we're measuring 2 observations on 1 student.
What
We're
would be
measuring,
matching, sorry.
a matching would be like if they said in fall of 2019, we measured these students and then we matched them with spring 2020 students on the same scale. Like we could match them on year in school, past statistics courses, GPA, and just matching them on certain characteristics. Does
Okay.
that make sense?
Yep.
Okay. So here we just give you the statistics. So we have our our sample size, the mean of the differences, and the standard deviation of the differences. And we're doing a post minus pre. So we're taking the post anxiety score minus the pre-anxiety score. And our research question is saying, do the data indicate that the anxiety levels decrease? So we would expect to see a negative value, right, for post minus pre, because we'd see a decrease. Our post scores would be lower than our pre scores. Does that make sense?
Yeah.
Mm-hmm.
All right, so because this is paired data, we're using mu sub d in our parameter notation. So looking at that, which of these hypotheses statements looks like the correct hypotheses?
B.
A.
I think one of you said A and one of you said B.
Yeah.
Yeah.
So it would be B, because remember we're doing post minus pre,
Right.
and we're hoping to see that the post score has decreased over the pre score. So if we have a smaller number minus a larger number, we'd see negative values. Does that make sense?
Mm-hmm.
Okay. When we create a simulation, so the simulation methods, we're flipping coins. You guys remember that from class where you flip a coin and decide, are you going, if it lands on heads, you're switching the values for the explanatory variable. So in class when we looked at the jumping jack bicycle kicks data, we switched, if it landed on heads, we switched the score for the bicycle kicks to jumping jacks and vice versa. If it lands on heads, we don't do anything. Does that ring a bell?
Yeah.
Okay, do you want me to write that out?
Yes, please.
All right. All right, so our sample size is 180. So we're gonna flip a coin 180 times. If it lands on heads, we're gonna switch the value, whoops, for post and pre-anxiety scores for that individual. If it lands on tails, we'll leave the same. So we don't move, we don't change anything. And then we're going to calculate and plot the mean difference. In anxiety score. For post minus pre. Okay. A conclusion is always written about the alternative hypothesis. So here we're trying to show that our post-course scores are lower than our pre-course scores on average. A p-value of 0.0053, is that strong evidence, little to no evidence?
Strong evidence.
Okay, so our choices here are sufficient or insufficient. So because it's strong, we know it can't be insufficient evidence. So the first one says there's sufficient evidence to believe the true mean post-course anxiety level is lower than the true mean pre-course anxiety level. What do you think about that one? Does that seem to reflect our study and the alternative for this study?
Yeah.
Yeah.
Okay. So it sounds like it. The one thing that I point out here is it says true mean and true mean. So this is looking at a difference in means. So this would work if it was independent data, but it's not independent data. And if you read the C, that also talks about the true mean is higher than the true mean. So that would also be, those both would reflect independent data. This one also has the wrong direction because it says higher. So the last option says there's sufficient evidence to believe the post-course anxiety level is lower than the pre-course anxiety level on average in the population of students. So here we're comparing the anxiety levels within a student and looking at the averages in our population. So that would be the correct conclusion for this study, because this is looking at mean difference. Does that make sense?
Yes. So how would it be like an independent, as you were saying, like for A and C?
So like if it was an independent study design?
Yeah.
So
So
we
how would
could-
I catch it like as independent?
So the reason I know these two are talking about independence is because it talks about true mean comparison to true mean. So that's looking at mu1 compared to mu2. In an independent study design, we would have two different separate groups. So if we wanted to look at students from one year compared to another year and we were just doing some sort of comparison between them, we'd say, well, their score is not going to affect somebody else's, so it'd be independent study design. Does that help?
Oh,
Understand that?
yeah.
Okay. All right, so interpreting the p-value, up here we're talking about, remember it's always the probability of our statistic, or more extreme if the null is true. So thinking about what we're looking at here, this is the probability. So if our null is true, if there is no true mean difference, in anxiety levels, for post-test minus pre-test scores. So if our null is true, the probability of observing a sample mean difference of negative 1.125. Let's go talk about where that came from really quick because we didn't really calculate it here. Or it's just this value right here, right? Or less, because we're doing a one-sided test, that comes from our alternative, is 0.0053 is our p-value. Pretty much a guaranteed test question that you'll have to interpret the p-value in some context on the final exam. So that is a paired study design. We could look at either difference in proportions or we have about 17 minutes left, so difference in proportions or difference in means. Anybody have a preference?
Could you go through like each one and do like I forget what it's called, like the
Theory.
the notation, you know, where it's like the HO, like
Oh.
the and then like mu1 minus mu2.
Okay, yeah, so let's jump back up here for a second. Well, we already talked about, I guess, the directions here, okay? So this is our null and alternative for paired. I was just seeing if I have, nope. Okay, so this is, we talked about this one being a difference in proportions. Do you want them just in symbols or do you want to talk about in words too?
Can you do both, please?
Yeah. So I'm going to write notation up here and then words down here because there's more room. So this is, remember we talked about this one already being a difference in proportions. So we're looking at pi 1 and pi 2 and we're looking at the relationship between those. So there's two ways you can write the null. You can write that they're equal or you could write that the difference in proportions is equal to 0. Because it's categorical, we're using pi, and because we're doing a comparison, we're using pi 1 and pi 2. For our alternative hypothesis, we have to look at our research questions. So here it says if we're testing to see that there is a difference in true proportions, does that indicate one side over the other, or is that a two-sided test?
So one, you said difference, right?
Yeah, it's just looking for a difference, so that's going to indicate two.
Oh yeah, that's two.
So, or we could talk about it being the difference, not equal to 0. So the easiest way to think about how we would write these out is thinking about what pi 1 and pi 2 represent. So anytime you're looking at Greek letters, you know you're talking about the true or the long run because it's a parameter. So we're looking at the true proportion of in group 1. So group 1 is high school. So I'm just going to put over here 1 is high school and 2 is college. So our group 1 represents the true proportion of high school people or people who have high school education who believe in evolution, and group 2 or pi 2 is the true proportion of people with college education who believe in evolution. So our null assumes there is no difference in true proportion of people who believe in evolution for high school educated. And college. And if we wrote out our our alternative hypothesis, the only thing that's going to change is that first part, because now I'm going to say there is a difference. Kind of for the sake of time and for space, I'm just going to write that line saying that the rest would be the same in true proportion of people who believe in evolution for high school educated and college educated. Does that make sense?
Yep.
Yeah.
Okay. So let's go look at another one to look at a different example of writing the null and alternative. Okay, so here we're talking about the fuel economy. So we're measuring the miles per gallon. And just seeing if, okay, so with this one, we're looking at independent groups. We talked about that already. So our null is going to assume the true mean, so pi 1 and pi 2, that they're equal or that the difference is equal to 0. And they're just looking at differences again. So this is going to be a two-sided test. So we're just trying to see, is there a difference in the true mean? And maybe just to, to help with understanding the hypotheses, we can think about our parameter of interest, because that's what we're using in our hypothesis statement. So here we're looking at the difference in true mean miles per gallon for cars manufactured in the US and cars manufactured in Japan. So we're taking group 1 is US and group 2 is Japan. And essentially you could take this statement about the parameter and set it equal to 0 for the null. So we could say the difference in true mean miles per gallon for cars manufactured in the US and cars manufactured in Japan is 0. And then for our alternative, we just say is not 0. Is that making sense?
Yeah.
Mm-hmm.
Okay. Let's see. I think I got a couple other examples just to take us all the way back thinking about single proportions. So in this study, it says 46% of all Americans watched the Super Bowl in February 2014. So this is actually our parameter value. So this is not a sample. So this is saying all Americans. So that's telling us it's about our parameter. So this is a single proportion. This is our statistic here. So in this study, when we're thinking about our null hypothesis, we only have one parameter. We just want to know what's the true proportion of US adults who watch the World Cup. And that we're going to assign a value of 46 or 0.46 versus an alternative where it's, again, difference of 0.46. I didn't know they were all two-sided. So now we're just talking about the true proportion of Americans who plan to watch the World Cup. So I'll write the null first. Is that making sense?
Mm-hmm.
And the alternative would just be not equal to, so the true proportion. Okay. Questions on that one?
Mm-mm.
Nope.
Okay, so then this one is looking at basketball. So Sergey, I don't know, Baca, I'm not a follower of basketball, averages 143.8 blocks per season over 7 years. So this is more, so this is looking kind of more at the idea of, so this is a single mean. So in this study, we're doing a comparison between two people. So here, if we were doing a calculation or a test here, we'd be comparing to the 185. This is more just looking at comparing confidence intervals. Just remember that when we talk about our single mean, we'd just be saying that mu is equal to some value or mu is not equal to some value. This isn't a very good example for talking about the single mean. But if we look at this study, this is looking at two quantitative variables. We're looking at heart rate and body temperature, which are both quantitative. So here we could test slope or we could test correlation. So if we were testing slope, we would test that beta, not beta 1. 217, we talk about it as beta 1. Beta is equal to 0 versus our alternative. I gotta look down to see what we're testing. So they're trying to show higher body temperatures cause higher heart rates. So this would be a greater than, because we're trying to show a positive association. If we talked about correlation, we use rho. Oops, not beta. What it's measuring is the linear relationship. So in words, we'd say that there is no true linear relationship between body heart rate and body temperature. I'll say body temperature. That's my explanatory. And then for the alternative for this one, try to figure out where to write it. We're testing that there is a true positive because we're looking at in greater than linear relationship. Between body temp and heart rate. I kind of took us through all those different types of studies, at least looking at the null and alternative hypothesis. Is there any one that you'd prefer or like to look at again, or look at some other parts too?
For that like equation right there, that heart rate,
Mm-hmm.
the slope is the slope the 2.44?
Yes.
Okay.
So then how would we like put the slope in interpret the slope in context?
Okay, so what it's looking at is as X, the body temperature increases by 1, the heart rate changes by our slope. So I'd say for a 1 degree Fahrenheit increase in body temperature, the predicted or estimated heart rate, either one, increases by 2.44 beats per minute. Okay, any other ones you'd like to look at?
I can't think of any.
Okay, so tonight I'll post the final key for this in Google Docs.
Okay, sweet.
Sounds good.
Thanks for coming.
Thank you.
Thank you.